Thank you, Mike, and thank you, Moss, for the invitation to come and talk to you about a topic that I think is very important for our state, our nation, the planet as well. And the topic is smart grids, energy security, renewable energy. I'll be talking primarily about the technology elements behind these areas, these topics, but not in any level of detail. So I won't show you any equations, not even any graphs. But to begin with, what I'd like to do is to just motivate the topic. And a lot of the interest in this area of renewable energy and smart grids started to arise maybe 2 decades ago, and it was a result of 3 particular issues and concerns we had with our energy system. And these concerns are indicated on this slide. So first of all, the first concern is energy security. We want to reduce our dependence on imported oil and gas. Right? And at that time, that was a major concern. Since then, of course, we've had the shale oil and shale gas boom domestically. So to some extent, that's been mitigated, but it remains a concern, as evidenced, for example, by the controversies about gas pipelines and oil pipelines from Canada. And down the future as well, of course, we do want to have our own energy sources for everything we do in the country. The second issue is economics. And energy cost for consumers, for industry, for businesses is, of course, a major concern. Again, if you go back 10, 15 years, we had very high prices relative to today for energy. And there were the projections from DOE were for those prices to continue to increase. I remember in I think it's exactly 10 years ago, the retail price, the wholesale price for natural gas was something like $7.50 per million BTU. Okay? Today, it's less than $3 per million BTU. But nonetheless, we all want cheaper energy. We want reliable energy at low cost. And the projections are, again, for energy costs to increase. So that's a second concern. And the third one, the last graph, the rightmost graph on this chart, relates to the energy use, and in particular, the use of fossil energy on the environment. And this has, of course, been a major concern globally for some time now. I started tracking this many years ago, and so this chart is actually relatively recent. And it shows, the data is from the National Oceanic and Atmospheric Administration, and they've collected data over the last 138 years, assessing the global temperatures over that time. And the 10 hottest years globally over that time have all been in the past 2 decades, so from 1998 on. And even worse, the 3 hottest years have been 2017, 2015, and 2016. Okay? So renewable energy and smart grids certainly are no panacea, but they are seen as an approach that can help mitigate all of these concerns. Okay? So we'll talk about that. But the issue is that it's not so easy to just take out all your energy sources, replace them with renewables. Renewables have certain characteristics that make them very different from the sort of energy sources we're used to. And the question is, how are you going to address those? So this chart tries to illustrate what the key difference is in enabling use of renewables compared to traditional ways of running a power system. So the top chart, the top graph, top picture, shows a traditional power system. So what happens in a traditional power system? Well, in a traditional power system, oil, gas, coal, to some extent nuclear as well, you have control over generation. You have complete control over generation. One thing to remember, by the way, whenever you talk about energy and talk about electricity in particular, which is what this chart is about, and in fact, most of my presentation is about electricity, is that the one thing to remember is that we have no effective, cost-efficient, scalable way of storing electricity. So in the grid, at any time, at any instant of time, all the electricity that's being generated must be consumed. Okay? Of course, this is a challenge, right? But we've addressed this challenge by being able to have controllable generation. So on the load side, when people flip switches or businesses start equipment, whatever, right? Of course, there's consumption happening. There are effects on consumption happening. at the generation side, that effect on consumption is instantaneously being detected just through the frequency of the line voltage. And based on the detection of the frequency, generation goes up or generation goes down. Right? So that's how we manage to keep the grid in balance, even though we don't really have control over loads, and loads are unpredictable as well. It's because we have perfect control, more or less perfect control over generation. What happens with renewables? Well, now we have wind and we have solar, and we do not have perfect control, and we cannot even in many cases accurately predict the generation that we will get from them. So obviously this creates a problem, right? How are you going to keep the grid balanced? We want to have more renewables, we want to be able to use more wind, more solar power, but the grid has to stay in balance. Well, the only way to achieve that is to now start putting control on the load side as well. Okay? So now we have to have sort of this twinned approach. There's some generation that is still more or less deterministic. There's some loads that are more or less deterministic, but then we have to have flexibility on both sides too. The saving grace here is information and computing and communication technologies. So things like wireless communications, for example, or low-cost sensors, or big data analytics, or cloud-hosted platforms. And we are now entering the age of the Internet of Things, as we often talk about now. That's what we can rely on to try and achieve the control that's depicted in this bottom picture. Okay? And so I'll show you 3 examples of technologies that are being developed for these. Again, they're sort of, the depictions here are not going to go into too much detail. Happy to go into more details if there's time or if there are questions. And in fact, in the first depiction, it's a cartoon, basically, right? So on the left-hand side of the cartoon is something called direct load control. And if you own a house, if you have central air conditioning, many of you are using direct load control already. So Xcel Energy and other utilities have programs where they will put a switch on your air conditioning unit, right? And on certain hot days during the summer, they have the right to cycle your air conditioning on and off. And the effect is the interior temperature of the home is going to be raised by a degree or two, depending on conditions. Right? And Xcel Energy or the utilities will do that based on whether they're having difficulty keeping the grid in balance, or whether they're seeing very high costs for electrical power as well. So that's one approach. But it's a very limited approach, right? It's basically for air conditioning. And perhaps more importantly, it gets the user out of the loop. So the user is no longer in control. The homeowner is not under control. Is not in control of this process. You may be throwing a party. You may have your boss over, and you know, I had a boss who didn't like to be seen sweating. You know, that could be quite a challenge in a case like this. So a much better solution is the cartoon on the right, which is automated demand response. And here, the homeowner is in control. And the idea here is that the utility gives a signal to an energy management system. And this energy management system has been programmed, scheduled, based on the signal being given. The signal could be a price signal, or it could be some other kind of signal too, to turn on and off loads or do other adjustments. This is used quite widely now, especially in commercial buildings where things will happen automatically, like turning on and off non-essential lighting, increasing or decreasing thermostat settings. If you're in a large commercial building with elevators, some of the elevators could be put on hold if energy needs to be consumed. It's also happening in homes in many cases too. But there's actually, we've kind of just scratched the surface with this technology, and more research is needed in order to be able to take it to where we need to take it. And this research includes things like, what is the right signal for a utility to give to get a certain level of consumption change, right? You want a precise level of consumption change, and you may give a price signal, but you're leaving the user in control. Well, you can statistically try and verify that and try and model that, but of course it's an issue. How do you incentivize users to do the right thing in a case like this? How do you classify and categorize the customer base, right? If this is a hospital, it's one thing. If it's a mall, it's another thing. If it's an office building, it's another thing. They have different needs, different types of equipment, and all of that. So many other interesting issues related to this topic. The second topic, microgrid optimization. To get an idea of what a microgrid is, think of the University of Minnesota campus as a microgrid. Right? The University of Minnesota campus has a large number of buildings. Right? It has many devices and loads that consume energy. It has heat and power generation facilities on site. It has some number of electric vehicles now, and in the future we'll have even more of them. And maybe in the future, those electric vehicles, the batteries of those electric vehicles will on demand be providing power back into the facility rather than just being charged. The charge and discharge capability will be there as well. Right? In addition, of course, the University of Minnesota campus is connected to the utility grid. And that utility grid, that connection is being moderated as well and controlled as well. And how much power you get from the utility versus how much power you generate on site is something that could be under your control. And right now, the facility management services at a place like the University of Minnesota will be managing and controlling all of these devices, making all these decisions. They'll use dashboards, they'll use various kinds of tools. But what they aren't doing today is really doing something that could be called truly optimal in some sense. And that's really an interesting area and an exciting area of research. And in order to do that, what do you need? Well, you need to develop mathematical models. You have to have mathematical models of all of the equipment. You have to be able to do some forecasting of the load that you are going to see over some horizon. The horizon might be the next few hours. It might be the next day. It might be over a week. Right? You will need to be estimating some generation forecast as well based on weather patterns. Right? You'll need information about utility pricing structures, which of course you have. And the idea is you have to put all of these into a mathematical formalism and a formulation and crunch that data and crunch those models to get the optimal way to operate the facility, all the while keeping into account the variety of uses of variety of services and uses that the University of Minnesota must provide, and the diversity of people that are here and their needs as well. Right, all of that those are constraints on the optimization. Microgrids exist now. A well-known example is the federal. The Food and Drug Administration microgrid, their large campus that they've recently constructed outside of Baltimore, Maryland. Honeywell, my previous employer, did the microgrid for that facility. Even in the first year or two, there was substantial savings in energy security, energy reliability, energy cost. The example that's often given is when Hurricane Sandy went through that area, the microgrid automatically detected, just based on fluctuations in the voltage, that there was some problem happening with the grid, and it automatically shut down the non-critical loads, started some generation, some manual effort involved there, did something with some of the loads and the storage that they had, and disconnected itself from the grid. So it islanded itself, and I was able to ride through that storm. And that the FDA facility is a very critical facility. There are many things that are safety critical and life critical that are happening in there, and you can't afford to just have the power go out. But it's really still a big area for research, and much more research needs to be done. I wouldn't, in fact, call that microgrid example I was just referring to as an optimized microgrid. There are some smaller examples of optimized microgrids. I know one that was done with Honeywell at a hospital in the Netherlands. And in fact, by the way, one of the leading researchers in the area of microgrid optimization is Professor Georgios Giannakis at the University of Minnesota. So that's technology number 2. And 3, I'll refer to the work that you were supposed to hear about, and you would have heard about in much more detail and much better than I can do justice to. And that's the work of Professor Siraj Tople on virtual oscillator control. And this work addresses the problem of connecting distributed energy resources that are in homes, that are in buildings, connecting them to the grid. Right? You have solar cells on rooftops. You now have electric vehicles. You have fuel cells coming into play. In fact, the number and the diversity of these distributed energy assets that are sitting in homes and facilities and not in the utility, that number and type are steadily increasing. One important factor with many of these and most of these devices is that they are DC devices. A solar panel generates DC power. It doesn't generate AC power. Your car battery takes DC input. It requires DC charging. Right? similarly with fuel cells. So what you have to do in order to connect these devices to the grid, and we want to connect them to the grid because we want these to, of course, feed the grid and be available to others in the grid to use as well, the energy coming from these sources, and conversely too. So these, in order to feed these to the grid, you have to synchronize them. You have to convert the DC to AC, and of course the conversion goes the other way when the charging is happening, and if it's something like a battery, right? So you have to convert the DC to the AC, and then it has to be synchronized with the phase of the grid. Right? And it's a difficult problem, and the current ways of doing it are inefficient, and they have time lags associated with them. It takes quite a bit of time for the power electronics to work and get the synchronization done. So Siraj's idea, and that he's been exploring quite successfully, is taking this notion of nonlinear virtual oscillators. So having a distributed set of devices, power electronic devices, that are automatically sensing minute changes in the grid and adjusting themselves in a way that is coordinated without being centrally coordinated, just in a distributed fashion. And that substantially alleviates these concerns with integration of these devices to the grid. And as you can see here, he's shown that you get 10 times faster synchronization of these distributed energy resources with the grid. So those were the 3 technology vignettes, let's call them, that I wanted to share with you. And now I'm going to go back to the motivations and what's been happening since, right? What's happening since we got onto this road, and of course much more needs to be done. But are we making good progress? Are we not making good progress? Are the problems still remaining, right? So here's first of all some good news. The left chart shows the cost of energy. In the cost of electricity, in fact, the levelized cost of electricity, and the levelized cost of electricity sort of is a way of normalizing electricity costs, so you're comparing apples with apples and not apples with mangoes or something, to refer to a fruit that's been on top of my mind lately. And what you can see from these charts is that wind, onshore wind, and photovoltaic systems, so PV, so solar cells, are now cost competitive with coal and natural gas. And furthermore, that the cost of these renewable generation technologies is going down, whereas the cost of coal and natural gas generation is going up. Right? So this is certainly good news. Right? The second chart, actually, I find this, to me, is particularly, I'm particularly fond of quoting this chart. And hey, look at that. Actually, I do have a graph here. And what this shows is, and we tend to assume that increasing the economy inevitably requires consuming more energy, using more energy. And that often has been the case. There's data that shows that. Historically, it's been the case. But it's very interesting. With all the emphasis on energy efficiency that's coming, that coupling perhaps is being broken. So over the last decade, the GDP of the US grew by 12%, but energy use overall dropped by 3.6%. Right? So if we can maintain this trend, that's also really, really good news. And lastly, you can see some power plant emissions have fallen down as well. But I wouldn't be giving you the whole story, and if I left you with any sort of feel-good notions, all right? So here's the not-so-good story. The right side of the chart you saw already, right? So again, it's showing the 3 hottest years over the last 138 years that NOAA has been collecting data. We're in the past 3 years. Right? The left side of the chart are CO2 readings, atmospheric CO2 readings. And the time axis on the horizontal axis is from 1700 till today. In fact, not till today. I downloaded this chart on June 8th, which was last Friday, so from 1700 to last Friday. Okay? And until about 1958, this data was estimated, the CO2, atmospheric CO2 concentrations was estimated by taking ice core samples. Okay? Since then, there's an observatory instrumentation at Mauna Loa in Hawaii, where on a regular basis, this data is being collected. It's available on the web. You can anytime go and look at it. And in fact, that's how I got this chart here. Right? So you can see that as industrialization progressed, CO2 emissions increased. But most dramatically, after World War II, all the growth that we've seen since then, those CO2 emissions have been really dramatic in their increase. I remember, this is now, again, going back maybe 15 years ago, when the scientific consensus was that 400 parts per million CO2 in atmosphere was really a threshold we should try not to cross. That at that point, the scientific consensus was that we would start to see some effects of global warming. Well, we've blown by the 400 ppm level. We are starting to see effects, and now people are thinking, well, can we maintain it to 450, and what impact is that going to have? Right? So that's why we need more and more research in areas like renewables, like smart grids. How do we reduce the CO2 footprint while we have energy security at the same time, and address the economics too? But technology is not the only part of the answer. In all of these areas, we can come up with new devices and new algorithms and new tools and new mathematics and new laboratories. But ultimately, to get impact, you need much more than technology. You have to think about the business models that would allow these technologies or products to be made and used broadly. The policies that would have to change. New standards that would need to be adopted. How to do things in a global context, because many of these challenges are truly global context, global challenges. Right? This is a chart that's, by the way, by a colleague of mine at the Technological Leadership Institute, which you'll hear about next, Kirk Frogat, and I kind of like sort of this notion that innovation is not just about technology. It's about more than technology. Often, certainly if it's engineering innovation or scientific innovation, technology is a core piece, but you can't think that that's all you need. Which leads me to my concluding slide. I'm with this organization called the Technological Leadership Institute, and I run a program within TLI called the Masters of Science in the Management of Technology, or MOT. It's kind of like an MBA in some ways, but it's oriented toward technologists. And you may think, why do we need a program that's focused on the management of technology? Well, the quote at the bottom hints at that, right? Technology has a huge impact on the economy. It's not just something we play around with or we could develop good devices with or have products with. The impact on the economy is tremendous. So you have to have effective ways of managing technology, of managing innovation, of taking ideas to practice, of figuring out what are the intricacies between policy and society and business and technology and research and all of that, right? So very intricate issues that need to be discussed. Our admissions director, Shea Moa, has a really wonderful blog on our website called "Which Shark Are You?" Okay, and it sort of refers to the MOT program and MBAs. And neither is better than the other. They both are serving very well certain audiences, the audiences they target, the students they target. But Shea's analogy is the following, that it depends a lot on how you approach new opportunities, how you approach new ideas. If you approach them from the mindset of a Kevin O'Leary, if you've watched Shark Tank, right? So you're really focused on the numbers, you're really systematic and rigorous about the finances, you're asking really good hard questions on that. The MBA will help you answer those questions and help you ask those right questions better than the MOT program will. But if you're approaching it from a technology lens and thinking about the technology piece and interested in that, which is more the Mark Cuban approach on Shark Tank, then we think the MOT program is a good one for you, for students who may be interested. So with that, I look forward to vague and cloudy questions at the appropriate time, and I'll hand it off to the next speaker. Thank you.